talking about sublinear time local access random generators.
I put every word possible in the title to confuse you. Okay, so the goal of this talk is to talk about what happens when you want to generate a huge random object, okay? And the question is, how can we generate these things? Do we need to generate the whole object up front, or can we generate the parts that we need locally on the fly, okay? So before I talk about the history of this problem, I want to just give an example. What about generating a really large random graph? So maybe I want to test my algorithm, I want to test it on random graphs, and I only need like parts of it. So I'll just generate the parts that I want of the adjacency matrix on the fly. Well, this seems great when you're talking about GNP and every entry is independent. But what happens, okay, I'm still generating. What happens if you have a requirement that it's symmetric? So there's a dependency. No big deal. You know, when I generate ij, I'll just write down the answer in ji. Okay, what about if I want to support like complicated queries, like what's the next neighbor? Because once I output what's the next neighbor, then I kind of made a lot of decisions along the way that could affect things that happen later on. So the point is there are going to be dependencies, and some of these dependencies could come from the model, and other dependencies could come from the types of queries you support. Okay, so I want to talk about some prior work. So let's start with just huge random objects in general. Huge pseudorandom functions were suggested, were studied and given in the incredible work of Goldreich, Goldwasser, and Micali. This was incredibly important in cryptography and complexity. It's something that gets used in pretty much everywhere. It was then Luby Rakoff, oh, Luby. Luby Rakoff looked at huge pseudorandom permutations. Noah Reingold looked at something called involutions, which I never knew what that meant, but I'll just tell you what it is. It's like a random pairing of points in the domain, so that f of x equals y, and f of y equals x. So kind of everybody's paired off. And just one other type of kind of hash function that was considered by Mansour, Rubinstein, Vardy, and Shi was looked at. And this is really a balls into bins type hash function, which is interesting because it's a process. It depends on throwing the ball into the bin that has the least number of balls in it. So it's actually a function that is somehow inherently sequential and in that sort of process, but it can actually be implemented locally as well, okay? Now, the model of implementing huge random objects was proposed, formalized, and first studied by Goldreich, Goldwasser, and Nussbaum in 2003. They looked at a number of types of objects, random functions, codes, graphs. They gave a bunch of important primitives. They showed, for example, how to sample from binomial distributions and interval sum queries for functions. There's another work that looked at that as well in the streaming literature by Gilbert et al. And one of they did a lot of things in this paper. It's a big paper. But one of the things that they talked about a lot in this paper is how to provide limited queries to random graphs with a specified property. So, for example, I want to present a random graph that has a Hamilton cycle in it, but appears like a random graph. Okay, so they focus on sort of indistinguishability under small number of queries in polynomial time. And even though they focus on that a lot, I want to say that they do present a lot of results that they don't need that focus. I mean, so they also have a lot of results in there. Okay, so let's just talk about graphs. So Goldreich, Goldwasser, and Nussbaum give some implementations of GNP graphs, this is what I just said, that have a specific property. I mentioned planted Hamilton cycle, but also they may have colorability, clique, connectedness, bipartiteness properties. The kind of queries they talk about in this work is mostly adjacency. This is one type of result from this paper. In this type of result, they talk about adjacency type queries. And there's usually some sort of limitation up to polylogarithmic. So the thing looks like a random graph that has a planted clique, as long as you don't take too many queries. There's a notion of truthfulness, so it will always have the planted clique. What the point is, it will look random. It may not actually be so random. Okay, another type of result that they give is for sparse graphs. The previous thing was also handled dense graphs and dense type queries, adjacency queries, but for sparse graphs, you don't want to store all ij. You also may want to talk about all neighbors, because in sparse graphs you have bounded degree. So in this case, they give a constructions of graphs that have degree at most polylogarithmic. They're indistinguishable from uniform distribution on a few queries, and here they support both adjacency and all neighbor type queries. Okay, all right. So Nussbaum actually looked at sparse GNP graphs. Here the degree is expected to be at most polylog. They probably wrote it as, for them they were thinking of constant, but you could, if in the constraints we'll give later, polylog works too. They support also adjacency and all neighbor. They bound the number of queries you're allowed to make in the paper, but actually their results, you can adapt their results so that this bound is not necessary in some settings, which I'll mention, and I'll say something more about it later in the talk. Okay, and another final work I want to mention about huge implementations of random graphs is a very recent work of Even-Levi-Medina-Rosen. And here they show how to implement Barabasi-Albert preferential attachment graphs. What's interesting about these graphs is they're kind of like these rooted tree forest structures, but they're generated by a very sequential random process. They're sparse, but the degree is not bounded. Okay, so it doesn't fall under the previous situations. They provide adjacency. They cannot provide all neighbor because the degree is unbounded, but they do provide something called next neighbor. Okay, so I've looked down the adjacency list of node I, and I've gotten up to a certain point, and I want to know what's the next neighbor. So they've implemented that type of query, and they give no bound on the number. So they will eventually reach, if you keep asking enough, they'll eventually generate the whole graph. If you ask for enough locations, they'll eventually generate the whole graph. But what's very interesting about this is that there was some process. Node I looks at all the previous nodes and picks one according to the degrees of the previous nodes. So how do you decide if I and j are connected? Or how do you find all the neighbors of node u? You would have to look at all the previous nodes to you and construct what their degrees would have been and what you would have picked. Or can you do something else? And they show that you can do something else, and you only need polylogarithmic many queries. Yeah?
So you're allowed to keep in memory all your previous answers.
Yeah, so the point is the queries are not, in order. Okay? The queries are, I want to know about the 57th node, and later I want to know about the millionth node, but I'm not going to go through all of them in order. My queries are arbitrary. And they show that you don't have to recreate the whole process of the graph. You just have to do polylogarithmic many time. You need only polylogarithmic amount of time to figure out what the previous things would have been.
In the number of queries?
What's that?
No, the time to answer any query is only polylog. So
in the number of nodes total in the graph.
Query, you cannot generate the whole graph because you don't have polynomial time. You only have
so it's like, think of it as an n-node graph, and they can get polylogarithmic time to do the queries. So what happens is they're not actually, there's not like one graph that they're simulating and figuring out what happened. They're making some choices, but they're doing it in a way that can be back consistent. And it's very beautiful, this work. I highly recommend it. So let me talk a bit about the models. So in the models proposed by Goldreich, Goldwasser, and Nussbaum about huge random graphs and objects, let's think for a bit as huge being exponential size. The user is not supposed to query more than a polynomial number of locations, although, and it's sufficient to generate a graph that looks random to a polynomial time algorithm. Sometimes some of their implementations actually give much more than this, and some of their definitions require more than this, but that is one of the ways to think of it. In the work of Even-Levi-Medina-Rosen, I would like to call it big instead of huge. Okay? These are big random graphs. Big is polynomial size. You might eventually write down the whole graph, but you don't want to pay the cost up front. So the end result should be random according to the claimed process, and not just pseudo-random, but actually random. Okay? So there would be some, it's kind of stronger as far as the end result, but weaker as far as the what the size of graphs that we need to handle are. Okay, so that's a little bit of a difference of the aims of these models. It's not to say that the results here and the results here are disjoint. That's not true, but this is just an attempt to kind of characterize the aims. Okay, all right. So sort of the standard. So let's compare also to the standard paradigm. In the standard paradigm, if I want to generate a random graph, I'm given some random bits, some random model parameters. We put it through the generation algorithm. You write down the big graph, and then the user interacts with this thing that got written down, right? But here, you're getting random bits and model parameters, and this generation algorithm doesn't do anything. It sort of interacts with the user. The user makes queries, and as there is a queries, things get written down in this side place. And the user gets response, and eventually this random object gets written down in memory. So the queries reveal partial information, and it's on the fly. Okay, so eventually the entire object is sampled and stored in memory.
The main requirement is consistency of the.
What's that?
The main requirement is the consistency.
It needs to be consistent, and the thing needs to come from the right distribution in the end. And not just appear random, but to actually be from that same distribution. Okay, so what we'd like is, we'd like to be able to answer the queries in polylogarithmic time. I'd like a succinct representation in the sense that if we have a degree d regular graph, I don't want to use n squared bits to describe it. Okay, we'd like to be consistent over future queries, so we do allow here to store past decisions, but eventually you need to give a valid sample. And we'd like distribution equivalence that we output something that's epsilon close in L1 distance to the goal distribution. And this issue of the what we're not going to talk about today is pseudorandom distributions. These are would be indistinguishable from the goal distribution or somehow preserve properties. We're not going to limit the number of queries, and we're not going to ask for a very succinct representation in the sense that, we're not thinking of the graph as being exponential size and we only get to store polynomial space. We're thinking of the graph as polynomial size. I can store it if I need to, but I just don't have the time to write everything down up front. That's sort of a different goal, okay? Yeah.
Yes, so the L1 distance, here you only care about a certain set of queries. So you don't care about all possible subsets to be closed. Just that on the queries you'll be closed. Isn't it a weaker notion than L1?
So that is the notion of GGN, what you're suggesting. And that may be sufficient in many cases, and then you would go to the definitions of GGN. Here, we're asking for pretty much the right, this epsilon close in L1 distance, this is really error that we get from implementation issues because we need to approximate these CDFs and sometimes we're a bit off. It's not really like that we're generating different graphs or missing something. Okay, so it's a little bit, or just generating a certain subset that looks random. So it's nothing like that. It's really just, it comes from the implementation issues that we didn't go to enough bits in generating our CDF. Okay? All right, so I want to talk a bit, before I get into the results, I want to talk about the types of queries. So what kinds of queries do people make from their graphs? Like Vertex-pair, queries is, your ask is edge u, v present. All neighbors, you might give node u and ask what are all the neighbors of u. Degree, you might ask what's the degree of u, what's the ith neighbor of u, what's the next neighbor of u, and you might even ask what's a random neighbor of u. Okay, so if you can do all neighbors, then you can do all the rest of these. But if you're not in a sparse graph, then these might be more complicated. So when your graph is not sparse, then I don't know what to do about these. Nobody has really studied these, so open question. Next neighbor was studied by these guys, by Evan et al., even when the graph is not sparse, as in the preferential attachment graphs. And we'll talk about it today in GNP as well. And we'll also talk about random neighbor for GNP. Okay, so what's nice about random neighbor is it allows you to take a random walk, even when you're in a large degree graph and you don't have the all neighbors query. Okay, so let's talk about some new generators. We're going to talk about GNP, stochastic block model, and small world graphs. Okay, so Vertex-pair query, easy. Okay, if I just want to support Vertex-pair queries, we'll just generate on the fly. We'll toss the coin as needed. You ask me if I and j are connected. I look there. If it wasn't tossed already, I'll toss a coin and write it down. Okay, so that one is easy. Okay, but what about sparse graphs? Okay, so I'm going to talk about an implementation that's really adapted from Noah and Nussbaum. Here, you're not going to go through the whole graph and fill in which ones are green and which ones are white, but what you could do is define the edges via ports. Okay, so for each node, you're going to pick a certain number of ports, depending on what its degree should be. And those will be those green guys. These are all the green guys are going to be the ports. Well, we don't know how to define this thing, but what we'll do is sort of pick the degree and give a number of ports equal to the degree of each of these nodes. And then to decide what the edges are, we'll match ports. So those red things here say that, okay, there's an edge between 5 and 3. Okay, so we'll just match ports. Okay, how do we do that? Well, first, it helps to notice that the following two processes can be made equivalent, okay? You can either pick the number of edges for each U. Think of this is G and P for small p, right? So just think about estimating how many, and just pick a random thing with the right distribution on how many edges each U has, and then sum it up to get the total number of edges. Or you could pick the total number of edges first, and then kind of divide it up among the U's, okay? And this means and how would you do that? Well, okay, I'll talk about this in a bit, but once you can do this, what it means is you can compute U's locations, where the locations are of U's ports. So you think of these green things as being actually one long list instead of nicely done like this, but you'd like to figure out which ones belong to node 5. So it turns out you can do this using interval summable functions by GGI-KMS and also GGN and everybody looked at those things, okay? So you can use those to figure out where U's locations should be. So then when you are given an all-neighbor query, let's say for node 6, what you can do is match its ports to other unmatched ports, okay? And I'm not going to fully describe that right now, but I'm going to talk about similar ideas later on and give more pictures for how to do that. But it's all using these notions of interval summable functions. First of all, you have to figure out where node 6's ports are, and then you have to have kind of a collection of the currently unmatched ports, and you need to pick from them randomly. And you can do it with interval summable functions. Yeah?
And you'll be able to ensure that you don't have parallel edges and self-loops, etc.
No, I don't. That's harder. I'm not going to do that.
So
yeah, I'm going to allow parallel edges and self-loops
so
in this particular implementation, yeah. Okay. Okay, yeah. All right. I will say that if you don't want the parallel edges and self-loops, then we'll do something else. Okay. So what about next neighbor query? Okay. So now, what is next neighbor? You query next neighbor on U. So you have figured out what the first 10 neighbors are for you, and you've figured out that, okay, it's connected to 1, it's connected to 3, it's connected to 10. What's the next neighbor, okay, along the adjacency list? So you're starting at the last found neighbor. If you're in the dense case, you can just flip coins until you toss a heads, right? Just go down the row. If it's already been tossed and it's a heads, great. But if it hasn't been tossed, toss the coin. Eventually, you'll see a heads. How long till you see a heads? These are all independent coin tosses, time 1 over p. Okay? So that's great, except that's great when p is constant, or at least 1 over polylog n. What do you do when p is little o of 1? Like 1 over square root n or something like that. All right. So you could use the all-neighbor query of Noah and Nussbaum that we just talked about. And that works when p is really, really small, like less than logarithmic in polylog in n, or divided by n. Okay, but there's a big gap between these two cases. And so right in the middle, square root n, okay? So think of that. So in this case, the idea is going to be, instead of just going down the row flipping coins until you find a 1, why don't we just sample the length of the zeros run according to the hypergeometric distribution. So that seems like easy enough. we should be able to do that. The only challenge is going to be that some of these entries were already filled in. Okay, so let's see what to do. So we're going to call this skip sampling. That's to pick the next neighbor queries. And let's think for a minute of a directed graphs. And let's also assume that nobody did any adjacency queries for us in the middle, that we're just doing next neighbor queries. I mean, everything can be handled, but it's messy. So let's just think, I mean, it's a little bit of a mess. Let's just think there's only next neighbor queries. That's all we're doing. Okay, and this is directed graphs. Okay, so we've done the next neighbor queries up to here. We figured all this out. Okay, so what we'll do is pick the length of the zero run according to a hypergeometric distribution. And how will we do that? We'll toss some, we'll pick a random number between 0 and 1 and do a binary search on the CDF of this thing. And once we pick the length of the zero run, we'll fill the next entry I. Okay, so we're picking, let's say we pick K. So we started at I comma J. We'll fill in I, J plus K with a 1. Okay, so we picked that there was a run of 4 zeros, and then the fifth thing is a 1. That's what we picked. Okay, so we'll fill this in with a 1. And that's the idea. That's the whole idea. So in this case, because it's directed, I don't have any worries that the other neighbors filled in any of these things. And also I made that assumption, very conveniently, that there were no vertex pair queries. Okay? All right, so this is good, kind of, except, does it bother anybody? What do you say?
Does it take too long to write all those zeros down?
Yeah, it takes too long to write down these zeros, okay? So that's a problem. We have to talk about that. Okay, so let me just answer. We're not going to write down those zeros. We're just going to write down the ones we see. Okay, so that's how this is what we're going to do. That's going to be like the theme here. We're worried about small p. There's going to be a lot of zeros and a lot less ones. We're just going to write down the ones. Okay, so that's how we're going to solve that. All right, so what do we do when it's an undirected graph? Okay, so here we have a similar thing. We picked the length of the zero run according to the hypergeometric distribution. We filled in the next entry. But this was already a 0. So is that okay? Well, so we have to talk about that, okay? So some of the nodes, like some of the locations here may have already been determined by the other neighbor. And if that's the case, we need to make sure we're still outputting according to the correct distribution, okay? And then there's this issue that Faith brought up. Do we need to write all the zeros? And I already answered that. I said, we're not going to write down all the zeros. We're only going to write down the ones, okay? And we have to talk about how we're going to write down the ones. All right. So here's how we're going to do it. For each node I, we're going to maintain the last seen neighbor J. So this is the last one we've seen so far. That means that everything before J has been determined, okay? But the way we're going to write down what came before J is we're only going to write down the locations of the ones, 2 and 6. And then implicitly, anything else is a 0 up to here, because everything up to here has been determined. So everything up to here is a 0 that's not in this list. Okay, now, the other thing we're going to do is we're going to keep track of the other ones out here that have been determined by other neighbors. All the ones out here we're going to keep as a min heap. So I always want to know which is the next one so far from the other neighbors. Okay? Now these zeros, maybe a lot of these zeros had been determined by the other neighbors. We will not keep track of that. And we'll show that most of the time we don't need to know which ones are zeros. Okay? So we're going to keep, so the zeros here we're not keeping track of. But the thing to notice is we can figure out if the neighbor made that into a 0. Because if the neighbor made that into a 0, that means the neighbor has been coming down and it's already reached past this row. Right? So we can just ask the neighbor, who are your ones? And if that is not one of the ones of the neighbor, then I know it has to be a 0. Okay? So we can figure out from the neighbor whether this is a 0 or a 1. All right. Good. So we keep track of the zeros implicitly, the ones explicitly, and these are in a min heap. There's a lot of question marks, too. So if the neighbor didn't call this a 0 or 1, it's a question mark. All right, so what are we going to do? So we do some skip sampling, and we choose K according to the geometric distribution. and we pick, we decide where the next one should go. Now I wrote that the next one should go here, but let's say I picked the next one should go here. That means past the min 1 in my min heap. This is the next one in our min heap. If I picked something that went past this min 1, forget it, just output this guy. Okay? All right. Now let's say I didn't pick something past, but maybe I picked something that landed on a 0 here. Maybe my neighbor thought it should be 0, and I picked that there should be a 1 landing right there. So that's not good because it conflicts with what my neighbor thought. Okay, we're going on the principle that the first person to toss the coin wins. Okay, so if I pick a 1 here, but my neighbor already decided it's a 0, then my neighbor wins, and it's a 0. It's not a 1. Okay, so what we're going to do, and it turns out this actually is okay to do, we're going to re-roll, starting here though. So starting here, we're going to pick another run length. And it turns out that works. Okay, the other possibility is when we started from here, we ran and picked a 1 right here, like in the picture. Okay, this is, we picked a 1 here, like in the picture, and let's see what happens there. Everything's fine. I had a 0 here, but the neighbor said it was already a 0, but it doesn't conflict with anything I chose, and okay. Is that okay? I don't know. We'll have to. I haven't really tried yet to convince you that this is the right distribution, but I'm just sort of telling you what the algorithm is for now. Okay? But what I want to mention that would not have happened is it's not possible that I went out here and that the neighbor had a 1 here. Because if the neighbor had a 1 here, we're going on the principle that whenever the neighbor picks something to be a 1, he has to tell us about it. Okay? So if he told us about it, it would have been on our min heap, and this would not have been our first one. This would have been our first one. We would have been told about it. Okay? So this is not a 1. This has to be a 0. But there's something kind of weird going on here because we're somehow re-picking certain random bits. Like we're retossing. It turns out that if you think about it, it's actually okay. Like if you're picking, if I'm picking the length of the run, it's kind of a fast way of tossing a bunch of coins in parallel. But if we go on the principle that each box could have 2 coins and the first one decides, okay, so I don't get, like already this coin was determined, so I flipped an extra coin, so what? It doesn't matter. It doesn't affect anything. But this had been tossed earlier and it was tossed completely uniformly. So it turns out that if you actually go through the analysis, it works out all right. I don't know if I'm going to be able to convince you that in the rest of this talk. So what I'm going to say is I'm going to give you an alternate way to do this in a few slides. But this actually works. Okay. So this y-correct distribution, I didn't really try to explain. I'm not going to. I'm going to leave it for another method. Yeah.
In terms of the guarantee you get, doesn't that give you an expected running number of queries that's polynomial?
Yes.
Okay.
Yes. This gives, yes. Yeah. Okay. So what I wanted to say, where are we now? We talked about the next neighbor. We said, okay, if the minute I toss a 1, so what's important here is I wanted you to see the ideas of the algorithm. It's important, every time you toss a 1, you have to tell your neighbor that he also got a 1 there, and he needs to store it somehow, okay? So we need to inform the neighbors, and what about the non-neighbors? Do we need to inform them with the zeros? Well, it turns out you can figure that out. So these are all things we can handle. What we didn't talk about but can be done is how to combine next neighbor and vertex-pair. So you need to keep track of a little bit more information if you do vertex-pair queries in addition to what we did. A careful analysis can mitigate all these issues, but what about the random neighbor query? How do we sample a random neighbor without knowing or committing to a degree? Okay, so we don't know the degree. All right, so in the dense case, no problem. Okay, in the dense case, we can I want a random neighbor of I, so just pick a random j. See if it's a neighbor. I mean, maybe it was decided already, and if not, I'll toss a new coin. And if it's not a neighbor, I'll try again, pick a new random j, until I find one that's a neighbor. And if this is dense enough, then the time is going to be pretty quick. It'll be time order 1 over p, so just like before. And again, we want to do little o of 1 over p. Also, in the sparse case, if we actually have all neighbor queries, we can just pick a random one of, after I got the all neighbor query, we can just pick a random one and say that's the random neighbor. Okay, so that's easy. What about the intermediate case that we just talked about? Okay, so the idea here is going to be to equipartition each row into contiguous buckets, and we're going to pick the sizes of these buckets so that the expected number of neighbors in each bucket is a constant. Okay, so with high probability, we're gonna pick it so that most of these buckets are non-empty, and furthermore, no bucket has more than logarithmically many neighbors. Okay, and so can we do this drum roll? Yes. If we can do this, then we can, instead of keeping track of all of the zeros and ones in the bucket, all we have to do is write down the logarithmically many neighbors in each bucket. So I only need log information per bucket to write down. Okay, well, how many buckets? So what I want to make clear here is we're going to have Pn buckets, each of size 1 over P. Okay, so when P is a constant, that's lots and lots of buckets. It's linear in n buckets, each one of constant size. In the sparse case, when P is like C over n, then we're going to have very small buckets. Okay, but let's just think of the case where P is 1 over square root n. You might have square root n buckets, so that's lots of buckets, and they might all be big because they might all be square root n size. Okay, so we don't have any notion that the number of buckets is small or that the size of the buckets are small. They're all too big for us. Okay? Okay, so what do we do with the bucketing? Now we've picked a size, so the expected number of neighbors in a bucket is theta of 1, and also order of log n with high probability. So the number of neighbors is roughly the number of buckets. Okay, so if I want to know, I want to know a random neighbor of V. We've taken its row on the adjacency matrix, kind of in our heads, and partitioned it into these buckets. What we're going to do is first pick a uniform random bucket and then fill the bucket if it hasn't been filled previously. Okay? What do we mean by fill? We said these buckets could be really big, so I really don't want to go down one by one and fill this bucket, right? So we'll talk about that. Okay, but in the end, once you fill the bucket, you're going to keep a list of the ones in the bucket. Remember, there's only logarithmically many of them. And then from that, we can just pick a neighbor inside the bucket very quickly. So step 2 is, once the bucket is filled and I've got this list of log n many ones, or at most log n many ones, pick one of those quickly, uniformly, okay? And now we have to decide, do we want to output this U, or do we want to, is this a good sample to output? Well, the problem is some of the buckets might have logarithmically many neighbors. Some of the buckets might have 0 or even just 1 neighbor. So if I picked a bucket that had lots of neighbors, then each one of those has a smaller probability of being output. And I want to pick uniformly. So we'll just do rejection sampling to fix this, right? We know that there's at most log n many neighbors per sample, so all we have to do is return U with probability number of neighbors in the bucket divided by log n. And if we don't return U, then just try again. Okay, so what's the probability we return neighbor U of this V? It's 1 over the number of buckets. We had to pick the right bucket in step 1. In step 2, we had to pick U from all the neighbors of V. So that's 1 over the number of neighbors in the bucket. And then we had this rejection sampling thing, which is number of neighbors in that bucket divided by theta log n. These guys cancel out. And remember that 1 over the number of buckets is like 1 over the number of neighbors. Okay? And it's the same for every U. So that's going to be omega 1 over log n times number of neighbors of V, where V is the original guy that we wanted a random neighbor of. So this is the right, 1 over the number of neighbors of V is the right distribution, but divided by log n. So what this means is the probability we return something in any loop is something like 1 in log n. And if you do this logarithmically many times, you're finally going to have something to output. And it's going to be uniform distribution. Okay, so that's the plan with the bucketing. Okay, so what we haven't described is how to fill this bucket. Okay, and it's good. This is why I did the previous slides, so that you can see here what to do. So the bucket might already have been indirectly filled in certain locations because of the neighbors. Okay, now what we're going to bank on is when those neighbors filled buckets, if they created any ones, they had to tell us about it. Okay, so any ones that neighbors stuck in our bucket, they have to tell us about. So we know those. So ones were reported when they were created. The 0 entries that neighbors might have stuck in our bucket, they didn't tell us about. But if we ever need to know if it was a 0 or 1, we're going to be able to figure it out from looking at the complementary bucket, the one that went kind of this way. All right? So what we're going to do first is just skip sample in the bucket, ignoring all the existing entries. Okay, so this is just on our own. We skip sampled. Okay, we had a run of length 2 followed by 1. Another, I mean, this is a terrible skip sample, but that's the slide. It's a run of length 2 followed by 1, run of length 2 followed by 1, a run of length 0 followed by 1, and so on. Okay, so that's how we filled this bucket. And now we go back and compare to what we knew. Now so what we want to do is something that only depends on the number of 1 entries in either here or here, okay? Because we know there aren't so many of them. We do not want to sit there and inspect every single 0, okay? So what we're going to do is, we knew we had some 1s that were attached to this bucket from the neighbors, okay? Go and take those 1s, these 2 1s here, and stick, what did I do? Oh, yeah, and just replace the bit that we chose. We chose something random, but they chose something random too. Okay, and they did it first, so just put it in there. Okay, and for each new green 1 entry, you remove it. Okay, so we had these guys. These guys just get replaced. Now, this was picked before this, so this needs to be a 0, right? All right, so what we're going to do is for each of our green 1s, there's only a small number of them, we're going to check, maybe it was supposed to have been a 0. And if it was and how do we check that? We go back here and check the neighbor. Did you fill it in? And what number did you give it? Okay, if they filled it in, then they either gave it a 1, in which case they agree with us, so we can keep it, or they gave it a 0, in which case we're going to change it. So where's an example of that? Here, we had a 1, but they gave it a 0, so we're changing this to a 0. Okay? Now the point is we only have to do this for the 1s we already had, which were only a constant number, and the 1s we newly generated, which is also only a constant number. So we don't have to spend much time, just a constant amount of time, to figure out what to fix on this. So the one thing you have to believe me is that it's okay if you toss a coin twice to just take the second coin. Okay. So now, why is this fast? The number of 1 entries is, okay, we said that. Good. So we're there. All right, so the nice fact is this bucketing idea also improves the next neighbor queries. Okay, so this is okay to do. All right, so I have a little bit of, do I have any time left? None, okay. So I'll just say stochastic block model. I think people have seen stochastic block model. Again, what we're gonna do here is, the difficulty here is we also have to pick for each node which community it's in, and we're going to use the multivariate hypergeometric distribution. This is something that was studied in other works, so I think I'm not going to show you, I don't have time to show you that. It's got another use, is that you can partially sample a random walk, but this is a really easy idea. If I want to know where a random walk is at time t, this is, again, it's a kind of a straightforward application of the distributions that all those other people showed how to do. We can figure out a position of a random walk at time t. This is a random walk that goes +1 with probability half, -1 with probability half, and these, these, what do you call these things? There's a word for it, that GGIKMS called it. These interval summable query functions will tell you, you can kind of figure out, so there's some random function, and you can figure out between I and j what's the sum of the function, and you can implement these queries in logarithmic time. And you can do it for a random function such that you only have to fill in the parts of the random function as needed, sort of. Okay, and with this you can kind of you can return query heights of a random walk that came from something that's possible to complete to something that looks random. Another thing one can look at is small world graphs. This is the model of Kleinberg, where you start with the grid, and then you add some directed long-range edges with probability c over the distance squared. So And what we're going to answer here, this is going to be a constant degree graph. So we'll answer all neighbor queries, which implies implementation for all the other queries we talked about. And here, the issue here is most Ds, you don't have these long-range edges for most distances. Okay? So what we're going to do is sort of use the CDF of the probability distribution on which distances you'd be far to pick which distances to put the edges at. And once I know that I have something at distance, say, 3, I'll go around all the edges of distance 3 and we'll skip sample them, okay, to figure out which ones get filled. Okay, and that's a way that you can do this without having to try all possible Ds. Okay, so future directions. What about other random objects? Many have been studied, but many haven't. And what about supporting degree and ith neighbor queries in more dense graphs? And what about local generation without history? So those are the questions, and thank you.
So is there any kind of